In this video, I'll show you how to find the definite integral using antiderivatives. We've been working with what we call the integral. In the previous unit, we worked with derivatives. So this formula right here states that if we take the derivative of some integral from a to x of f of t dt, that is equal to f of x. So notice it's not f of t anymore. I substituted the upper bound in where x is. This means that the integral is an antiderivative of f, a fact that we can exploit in the following way. So we have the f, capital F, is any antiderivative of lowercase f, then if we have this function from a to x of f of t dt, that'll be equal to f of x plus c. Capital F is the antiderivative. So let me give you a quick example of what I mean by that. In the previous unit, we learned about derivatives, and we learned that the derivative of sine of x is equal to cosine of x. Well, the antiderivative goes backwards. So this means that the antiderivative of cosine of x is equal to sine x. So we're basically saying, what can I take the derivative of to get this function? Now we're going to take this a little bit further. I'm going to substitute this upper bound x for a. So now I'm going to have the integral from a to a of f of t dt is equal to, like I did up here, I'm going to take the upper bound and plug it into here. So I have the antiderivative of a plus c. C just being some constant. Well, we know that the integral from a to a is equal to 0. That was one of our integral rules. So this is equal to f of a plus c. I just carried all that down. So now I'm going to solve for c. So I'm going to subtract f of a from each side. So I end up with c is equal to negative f of a. I'm going to use that to plug this piece back into here. So I end up with, starting from the very beginning here, the integral from a to x of f of t dt is equal to f of x from up here. Now c, I'm going to replace with negative f of a, so minus f of a. This is going to be very useful in this section and in the sections to follow. So it says, to evaluate this integral, we use the antiderivative of x, or of our upper bound, minus the antiderivative of our lower bound. Here's an example. We want to find the integral from 0 to pi of sine x dx using this formula that we just derived. So off to the side, I'm going to recall that the derivative of cosine of x is equal to negative sine x. Well, I don't want negative sine x, I want positive sine x. So the derivative of negative cosine of x will give us positive sine x. So what we're looking for is, what can we take the derivative of to get this function? That's called the antiderivative. So the antiderivative of sine of x is negative cosine x. So now using this function, or this formula, I'm going to take the antiderivative evaluated at the upper bound. So the antiderivative is negative cosine of x. So I'm going to do negative cosine of our upper bound minus the antiderivative at our lower bound. So our antiderivative, again, is negative cosine x. So minus negative cosine of the lower bound. Cosine of pi is -1. The negative out front just carries down. Negative cosine of 0 is also -1. The negatives cancel out, so this becomes 1 plus 1, which is 2. So the integral from 0 to pi of sine of x dx is equal to 2. That is the area under the function